Hi everyone, good afternoon. For some people, maybe it's good morning or good evening. My name is Thiago Souza. I'm a civil and geotechnical engineer in South America area, and I'm from Brazil. Today, we have a very interesting webinar with Dr. Peter Robertson. Before his lecture, I would like to present Geotecnia Brazil for you. Geotecnia Brazil is a young voluntary community from Brazil, created in May 2019 to unite geotechnical professionals from all over the country and now Latin America in social media. We have people from Europe, Africa, Asia, and I would like to thank all the people in the Brazilian Association of Soil Mechanics, ABMS, for the support. So, about the lecture today, it's very special for us. Peter Robertson has over 30 years experience as an educator, researcher, consultant. He's from England. He's civil engineer, and his master degree and doctoral degree is from University of British Columbia. His mentor was Campanella. He has expertise in situ test of soils, earthquake design of geotechnical structures, soil liquefaction, and biodesign. He was the principal investigator of the Canadian liquefaction experiments, CANLEX, from 1993 to 2000. Dr. Robertson has been a consultant to various industrial clients and insurance companies in North America, Asia, and Europe for projects involving liquefaction evaluation, stability of onshore and offshore structures, landslides, stability of natural slopes and tile dams, deep foundations, and the use and interpretation of in situ tests. Dr. Robertson, thank you very much for your presence here. It's a big pleasure for us, and it's a great honor for me to introduce you.
Diego, thank you. It's my pleasure to be here, and I'll just bring up the slides so you can see the title of the presentation. And I thought it was timely that I should talk about flow liquefaction, given the recent tailings dam failures in Brazil. And so I wanted the talk to really be about, so what is flow, or sometimes referred to as static liquefaction, and how do we evaluate the risk? And I've posed the presentation as a series of questions. So first of all, we'll talk about what is flow liquefaction, and then we'll talk about what is the cause of the strength loss that's the primary driver for it. And then why can sands experience this sudden undrained strength loss? And then what can trigger this strength loss? And how do we evaluate the potential of strength loss? And what is the risk of instability? And then some summary slides. So I do want to cover quite a bit of material, so I will move along relatively quickly. But of course, the advantage this will be recorded, and you will have the ability to eventually watch the recording and replay parts of it if you look for more clarification. So let's start off in terms of what is flow, or as I said, sometimes referred to as static liquefaction. I tend to prefer the term flow liquefaction because sometimes earthquakes can trigger flow liquefaction, and therefore it can be sometimes confusing to think of it only as a static trigger. So hence I'll use the term flow liquefaction. But essentially it's this sudden and significant strength loss resulting in a flow failure. And there have been several major examples. I'm only going to talk about a few. One of the earliest was actually the Quick Clay landslide in Norway back in the late 1970s. And it's recognized as the Risa landslide. And there are videos on YouTube that you can see what this landslide looked like. Fortunately, it was captured on a home video by several people. And that was in a quick, highly sensitive clay. But more recently, they've tended to occur in tailings dams, and one of the early major ones was the Stava tailings dam in northern Italy in 1984, and then more recently was the Fundão tailings dam in 2015, and then just last year with the Feijão tailings dam near Brumadinho. And I'll refer to the Feijão tailings dam. I won't mention the investigation. I've given the link to the report, and the details are there. I just wanted to show some images of the failure just to illustrate how rapid these failures occur. And rather than show the video, I've selected to show some still images from the video. And the time is in the top right-hand corner. So within a few seconds, the failure starts and it bulges, drops at the top, and then rapidly begins to fail and move out very quickly. And within 10 seconds, the failure has occurred across most of the dam. The initial failure is relatively shallow. And then after the initial failure, when that failed mass moves out very rapidly, there were subsequent relatively shallow failures that retrogressed into the tailings. And within a period of about 5 minutes, most of the tailings were removed from the tailings storage facility. So if you look at case histories in general, there's been a number of them, and I show a sort of an image there of the Stava tailings dam failure in 85, and then the Fundão one below. And the common features are generally the deposits are very young. In terms of geologic age, they're very young. They're all Holocene or younger. And of course, the tailings dams, those are exceptionally young. They're in the order of just a few decades of age, 10 or 20 or maybe 30 years of old, which in geologic age, of course, is extremely young. They're generally non-plastic or low plastic materials. Even the quick clay in Scandinavia was a low plastic clay. There's generally little or no stress history. They're all very loose. They're contractive at large strains. And generally, they're relatively low effective confining pressures, generally less than about 3 atmospheres. They're not occurring under high overburden pressures. Common features of the instability is that some of them are triggered by very minor disturbances. The failures tend to occur without warning, as that video we showed the still images illustrate. And the failures tend to be progressive and extremely rapid, again, as the Feijão tailings dam failure illustrated. And in tailings dams, often the observation method is used, and the observation method becomes less valid when you're looking at flow liquefaction, because the failures occur so rapidly that there's no time to respond. And so it becomes really a major design issue for tailings dams. And so much of what I'm going to say is really focused on those sorts of structures. So when we look at the strength loss in undrained shear, most of us are aware that when you shear soils, they tend to move towards a critical state. And the locus of those critical state makes up a critical state line. Here it's illustrated in terms of void ratio against log mean effective stress, and it's illustrated as a simple straight line. And so soils can be either on the loose or contractive side, or they can be on the dense dilative side. So if a material is on the loose contractive side, that means if you shear it drained, it will tend to contract down to critical state. But if it's sheared undrained, then that contraction induces a buildup of pore pressure. That buildup in pore pressure decreases the effective stress, and the stress path will move towards critical state at constant void ratio, but decreasing effective stress. And if you look at the strength envelope, soils are essentially frictional in nature, and so the drain strength goes directly up to the strength envelope. But if the stress path moves to the left, with increasing pore pressure and decreasing effective stress, then eventually the undrained strength is significantly smaller than the drained strength. And so for contractive soils, the undrained strength ratio is less than the tangent of the friction angle. But also, it depends on the slope of the critical state line. The flatter the critical state line for a given state of contractiveness, you'll get a bigger buildup of pore pressure and a larger decrease in strength. So the undrained strength can actually drop to an extremely low level. And that's often referred to as the liquefied undrained strength or the residual undrained strength. For sandy soils, we tend to use the term liquefied undrained strength, and for clay soils, we tend to use residual. But it's the undrained strength that's mobilized at very large strains. And for some soils, that can be an extremely small number when the critical state line is very flat. And Bean and Jeffries really promoted the idea that we could understand this by defining a state parameter, and it's the distance away from the critical state in terms of void ratio. But actually, a slightly better term would be the stress ratio, which is the ratio of the current mean effective stress to the mean effective stress at critical state. And that's a sort of a direct measure of how much strength loss would occur. And they're linked, so the stress ratio is linked to the state parameter via the slope of the critical state line. And Bean and Jeffries described that in detail in their book. Now, if I illustrate critical state line over a wider stress range, we observe that the critical state line is not a simple straight line. It actually curves at higher stresses. And here I've illustrated two. So Toyora sand is sort of a sub-rounded silica sand, and you can see the curvature occurs at very high stresses. And I've chosen here to represent the plot in terms of normalized mean effective stress, normalized by atmospheric pressure. So 1 is 100 kPa and 10 would be 1000 kPa. And then on the vertical axis, instead of void ratio, I've sort of normalized it as relative density. And that sort of normalizes all the data from various sands. It's not the ideal way to do it because relative density has uncertainty in terms of how you determine Emin and Emax, etc. But I wanted to illustrate this because Bolton's empirical approach of stress dilatancy, he used it as a way to estimate the peak friction angle as a function of dilatancy. And if you put dilatancy to 0, then you can actually draw the critical state line using Bolton's empirical relationship. And that's what these two dashed lines are for different levels of mineralogy parameter Q that Bolton has suggested. And he has suggested a value of 10 for most silica sands and 7 and smaller for more compressible sands. And you can see here that Bolton's relationship actually matches very well with the laboratory data, which in a way you would expect because Bolton, of course, based his empirical relationship on extensive laboratory data. So it's not surprising that the two agree. But I show it here as a way of illustrating how much curvature can occur in the critical state line. So if I now go to an example, and in Bean and Jeffries' excellent book on liquefaction using a critical state approach, they show data from many different sands, but they show extensive data for Erksack sand, and that's what I've shown here. And so you can see the critical state line curving. It's actually quite similar to the one for Toyora sand. But they tested a large number of samples over a wide range of void ratios and stress levels. And so they were able to also determine the limiting compression line, which is the loosest state that they could make the sand. And I've illustrated in dashed here a range of consolidation lines, initially extremely loose, consolidating over to its loosest state, and then coming down the limiting compression curve. And then sort of a medium dense sand that would be initially dilative, but eventually crossing over, becoming contractive as the dilatancy is subdued, and then coming down the limiting compression curve. So all sands will eventually become contractive at high enough stresses. But if we look at three samples, now I presented a short paper at a conference in Vancouver in 2017 that outlined this in a little bit more detail, but I'm just illustrating here three samples A, B, and C. They're all at their loosest consolidation state, but at different confining pressures. Sample A is at a relatively low confining pressure at a very loose state. And if it's loaded undrained, there was a significant loss of strength as it moved towards its critical state. And in the corner here, I'm illustrating what I'm going to refer to as the strength loss index. It's actually the same as what Bishop defined as the brittleness index. I prefer not to use the word brittleness because brittleness implies not only the amount of strength loss, but how quickly the strength loss occurs in terms of straining. So I prefer to use the term strength loss, and that's what I'm going to use here. But it is the same term that Bishop had suggested many years ago. And it essentially is an index of how much strength loss occurs. And so if you lose 90% of the strength, then this strength loss index becomes 0.9 or 90%. So sample A loses 90% of its strength. Sample B, which has a looser state in terms of state parameter, will only lose 40% of its strength. And sample C, which is even looser still in terms of defining it by state parameter, but only loses 20%. So 3 samples, they're at their loosest state, but as the confining stress increases, they show less strength loss. So sands show less strength loss with increasing confining pressure. So this sort of illustrates that the most dangerous area are very loose, saturated soils at low confining pressure, where there's the potential for very significant strength loss. At higher confining pressure, the strength loss potential decreases somewhat. So we'll keep that in mind and come back to that later. So what can cause sands to experience this sudden strength loss and behave undrained? Because sometimes these are relatively clean sands and yet they behave undrained. And so what really happens is if the contractive volume change occurs extremely rapidly, the pore water may not have time to drain, resulting in undrained shear. So it's not controlled by the rate of loading, it's more controlled by the rate of volume change. And so traditionally we tend to think of either slow or quick loading, but it's really the type of loading that induces contraction. And if large volumes of the material can experience this contraction and the water does not have time to fully drain, then suddenly it can switch over to undrained shear and hence show significant strength loss. So slow drained loading, such as a rising groundwater level, can trigger sudden undrained response. So it doesn't necessarily require undrained loading to trigger the undrained response. You can have slow drained loading trigger this. And we published a paper a little over 20 years ago doing laboratory testing to illustrate that when I was at the University of Alberta. And so what can trigger the strength loss? And here I've taken a very nice diagram from Olsen and Stark in 2003. And it basically says any shearing that induces contractive behavior could trigger this strength loss. And Olsen and Stark showed 3 stress paths. On the left, it's got the stress strain curve, with a peak and then dropping to a liquefied undrained strength. And on the right is the stress path. They refer to a yield strength envelope and then eventually to the failure envelope. But if you start off at point A, then traditional sort of undrained loading like rapid construction would follow a stress path that would go A, B, and C. So it would rise up to its peak undrained strength and then strain soften down to its liquefied undrained strength. Or of course, if you had an earthquake, it could start off, here it's referred to as A prime, and the cyclic loading from the earthquake would move it across, and then undrained strain softening would response, and it would drop down to its liquefied undrained strength. But you can also have slow unloading, such as the stress path A to D, such as an increase in groundwater level. So if you have a slope and you've got a piezometric surface within the slope, and that piezometric surface can increase, then the shear stresses stay essentially constant, but the mean effective stress decreases, and so the stress path will move slowly to the left, and it can do so in a drained manner until eventually it hits the yield surface, and then suddenly undrained collapse can occur, and it moves to the liquefied undrained strength. So there can be many different triggers that can trigger this undrained strength loss. So what conditions are required for instability to occur due to flow liquefaction? So essentially, you must have loose, saturated, or at least near saturated soils that are contractive and strain softening at large strains. The shear stresses in the slope must be relatively large relative to the liquefied undrained strength. They must be larger. And then you must have some events or event that could trigger the strength loss. You must have a sufficient volume of the loose saturated soils for instability to manifest. And then, of course, you must have a geometry that enables instability to actually occur. And of course, that's why tailings dams tend to be susceptible to this. They often have relatively steep slopes. They sometimes have a relatively high phreatic surface in the tailings dam. And if you've got loose saturated tailings, then where the liquefied undrained strength could be less than the static driving stress, then you have all of the components there. So then the next question is, how do we evaluate susceptibility? And since they tend to occur in very loose soils that are either non or low plastic, these are soils that are also extremely difficult to sample in a truly undisturbed manner. So in situ testing is often preferred, at least in the initial stages, combined with some laboratory testing. And certainly the cone penetration test with pore pressure measurements, the CPTU or the seismic CPTU, is preferred because it's rapid, it's cost effective, it provides a continuous profile, it's highly repeatable, and we also have extensive experience with case histories. And from the CPT, we can estimate whether or not soils are contractive at large strains. We can measure the in situ pore pressure, so we can determine what the piezometric profile is like, which is what we need to calculate the effective overburden pressure. We can do that through dissipation tests, and the rate at which the pore pressure dissipates tells us also a lot about the drainage conditions of the material and whether or not the CPT itself was being carried out under undrained or fully drained conditions. We can also evaluate the variability or the extent of the contractive material, because the CPT provides continuous profiles and you can do quite a lot of them relatively cost effectively. And you can also estimate whether or not there's any significant microstructure, such as any aging effects or cementation from bonding, and that requires the shear wave velocity as an additional measurement. We won't have time to talk about that in detail, but I did publish a paper in the Canadian Journal in 2016 that outlined how you would go about doing that. And then, of course, ideally you need some sampling to do index testing, so you can determine the grain size characteristics and the plasticity of the material. Also look at the mineralogy. Ideally do some X-ray diffraction so you can look at the mineralogy in more detail, and then take disturbed samples and make reconstituted samples to determine the critical state line. So there's a number of CPT-based methods. Probably one of the first was by Howard Plewis and his colleagues, Jeffries and Mike Davies. And that was in 1992. And that was built around the state parameter approach using the CPT. And then Olson and Stark developed a method, and Sadr Karimi has published a few updates on that method. And then, of course, Jeffries and Bean have given their updates, and in their book that was updated in 2016, give extensive detail of their methodology. And then in 2010, I published a method as well. And so most of them are based mainly on sand-like data, where the CPT penetration process is predominantly drained. And each of the methods uses slightly different normalization techniques to normalize the CPT tip resistance to account for effective overburden pressure. And most of the methods, Pluis, Jeffries, and myself, we all used a normalization that also was dimensionless. The one criticism a little bit with the Olsen and Stark approach is that they didn't dimensionalize it, so it's actually in megapascals, so you have to be aware that it's not fully dimensional. Now, given the time constraints, I'll just, of course, reference my own approach and give you the outline of that. And so in 2010, I looked at a number of case histories and narrowed them down to about 6 that had sort of modern electric CPT data, and here they're listed on the right-hand side. And I was able to plot essentially most of the CPT data, not just in terms of the mean value, but essentially the mean plus or minus the standard deviation. So it shows as a sort of an oval on the soil behavior type plot of normalized cone resistance against normalized friction ratio. And you see the 6 case histories. And Pluis and Bean and Jeffries had suggested a boundary for state parameter, and I had said that that boundary could be represented by a clean sand equivalent of 70, and all of those case histories plot below that, which is consistent with the Pluis boundary, consistent with the Bean and Jeffries boundary, and of course consistent with the one I had suggested. And following on from that, I then linked it to the liquefied undrained strength and said that for sandy soils, you could actually estimate the liquefied undrained strength ratio from this normalized clean sand equivalent. And you can see that all of the case histories have liquefied undrained strengths averaging about 0.1 and all less than 0.15. So the undrained strength ratios are relatively low. But in that paper, right near the end of the paper, I did comment and said that the proposed relationship can be conservatively low in sensitive clays, where the remolded shear strength can be defined by the sleeve friction, or the remolded undrained shear strength ratio is the sleeve friction from the cone divided by the vertical effective stress. And that was recognizing that these relationships were primarily for sandy soils, where the penetration process is essentially drained. But when you get into clay soils and the CPT penetration process is undrained, then we can switch over to the more traditional ways of estimating the remolded undrained strength of clays. But I've noticed in practice that most people have not really followed that final note. And to be fair, it was only a small note near the end of the paper, and I didn't define exactly the limits of when you should start to switch over to this alternative relationship. And so recently, I've decided to update the relationship to help users understand when to switch over. And so in 2016, I updated the soil behavior type chart to be more generic. And I put in this boundary line that would define dilative materials above it from contractive materials below. And I gave it a little bit more curvature going into the clay region. And here in red, I've identified that in the sand-like materials, which are sand-like dilative and sand-like contractive, they're predominantly drained during the CPT penetration process. And when you get into the clay-like region, the CPT is essentially undrained during the penetration process. And then I identified this sort of transition material where the CPT penetration process was partially drained. And here I've highlighted, it's roughly from an IC of about 2.6 to about 3. And so in that middle region, you can get partial drainage. And also keep in mind, this chart is for soils with little or no microstructure, so young, unbonded materials. So to calculate that clean sand equivalent, Catherine Wright and I, back in 1998, for cyclic resistance, for cyclic liquefaction, we had suggested that you could calculate this clean sand equivalent by taking the normalized cone resistance and multiplying it by a correction factor, which in the early days was often referred to as sort of a fines content correction. I think more increasingly people recognize that it's really a correction factor to account for compressibility of the soil. And so we had suggested that this correction factor was a function of IC, and essentially there was no correction in clean sands where IC is less than about 1.6. But as IC increases, as you move towards the silty sand region, then you'd need to make a correction. But I've recognized now that once you get to around 2.5 or 2.6, there is the risk of partial drainage during the CPT. And so the original correction factors don't directly work as well, and they don't link so well to when you get to fully undrained behavior with the CPT when IC is greater than 3. So I'm suggesting an update. You can see it makes no difference at values less than 2.5 and very little difference less than 2.6. So it makes very little difference to the evaluation of cyclic liquefaction, which generally stops at a value of 2.6. But it makes a bigger difference once you extend it into the clay-like region. And so if you take that and then update the relationship for the large strain, liquefied, undrained strength ratio, here I'm generically calling it just the large strain shear strength ratio, because I'm also going to show the drain strength. And so now you can see I've expanded the scale from 0 all the way up to 0.8 as an undrained strength ratio. And I show the case histories from the 2010 publication. They're still down here, the Class A and Class B case histories. And I've simplified and updated the relationship, because the relationship in the original publication does not extend very well. There's a glitch in the relationship when you start extending it past a strength ratio of 0.3. So I've simplified and updated the relationship, and I've said that it applies specifically when IC is less than 3 and the effective overburden pressure is less than 3 atmospheres or 300 kPa. And so you can see I've extended it all the way up now, and now I'm illustrating that when you get into the dilative region, when the sands are now dilative at large strains, this is where the drain strength applies. And so now I begin to show some lines that are a function of the peak friction angle, which is controlled by the constant volume friction angle. So there isn't a single line, there's a family of lines depending on the constant volume friction angle. And so you can see that it's a simplified relationship, but extends all the way up. And previously I had said that a clean sand equivalent less than 70 would be contractive. And you can see that there is sort of a transitional period where there's partial contractive, where it initially contracts, but then begins to dilate, but is not necessarily fully dilative by the end of shearing. So you have that little zone of transition there. And I've also shown to show in a dashed line here the approximate location of the peak or yield undrained strength ratio that Olsen and Stark have suggested, just to illustrate that its approximate location in there. So you can get a relative sense of, you've got the peak drain strength way up here, and then once you get into contractive materials, the liquefied undrained strength can drop to extremely low values at low confining pressure, and significantly less than the peak or yield undrained strength ratio. Now, if I take all of that together, you can actually plot contours of the liquefied undrained strength ratio onto the soil behavior type chart. And I find this a useful exercise, because often people will plot CPT data onto the chart. And so if you've got an overlay of these contours, you can immediately get a sense of what the liquefied undrained strength ratio would be. And so it's a small difference from the original clean sand equivalent curves, where they just curve down a little bit more, and then they tie into the straight line relationships in the clay-like region, which is controlled by the sleeve friction. So these straight line portions here are where the liquefied undrained strength ratio is just simply equal to the sleeve friction divided by the vertical effective stress. So that's what they look like. And they're based primarily on case histories and lab data of soils with little or no microstructure and at relatively low confining pressure. Now, when you look at the case histories, I commented earlier that all of the case histories had back calculated liquefied undrained strength ratios of 0.15 or less, with most around a liquefied undrained strength of 0.1. Now, if you look at the data here, it's data modified from Sadr, Karimi, and Olson of the critical state undrained strength ratio as a function of the strength loss index. And when you put the case histories in there, you see that the case histories must all have had strength loss greater than about 40%. So a significant amount of strength loss was occurring. Now, if you take that, so if I draw the contour of that 0.15 undrained strength ratio, and I've shaded it in here, so it says in this region, this is where you would expect the greatest amount of strength loss. So anything that plots within that shaded area, there'll be significant strength loss. Now, there is a region over here where clay-like materials can be contractive at large strains, but not necessarily strain softening, or with very little strength loss occurring. So there is a contractive region with very little strength loss compared to the sort of the sensitive clay region where there's significant strength loss. So I find this a very useful way to look at CPT data with these contours. And if you look at the case histories, here's the Fundao data, predominantly for the coarse tailings, and it plots with most of the data into that a large strength loss region. And here's the data from Feijão tailings dam, both the coarse tailings, which tended to plot higher up here in the sand-like region, and then the fine tailings that plotted in the clay-like region where the CPT process was undrained. So the coarse tailings, the CPT penetration was drained, and the fine tailings, the CPT process was undrained. So let's talk a little bit about the risk of instability. And ideally, the way to evaluate that is you can perform limit equilibrium analysis using the liquefied large strain undrained strength ratio. And if the factor of safety is greater than 1, then clearly the risk of instability is extremely low and generally acceptable. If the factor of safety using the liquefied undrained strength is significantly less than 1, then there's a risk of instability and the risk is high. In other words, there could be significant strength loss, and the risk of instability is very high. Now, if the factor of safety is close to 1, but slightly less, then the risk is smaller, but still exists. And what that means is that if instability were to occur, the inertia forces would be much smaller because the factor of safety is quite close to 1. Compared to when the factor of safety is significantly less than 1, then there are large inertia forces. And once instability manifests, then the thing can rapidly get out of control and move quickly. The other observation is that low plastic soils tend to be more brittle at low strain, at low stresses in undrained shear, and that bonded soils also tend to be very brittle due to the small strains to trigger strength loss. And I'll illustrate that shortly. So when we look at the risk, here I've tried to illustrate in some simple diagrams. So I've illustrated a slope here, a relatively steep slope that's got a high phreatic surface, and we're looking at an element of soil. And I show both the stress strain curve as well as the stress path in terms of shear stress against mean normal stress with the failure envelope. And because the slope is relatively steep, the initial shear stresses in the slope are high. And so I've illustrated 3 stress strain curves, one where there is no strength loss in undrained shear, so the strength loss index is 0, another one where there's only 20% strength loss, and another one where there's 60% strength loss. And you can see just by comparing the initial static shear with the liquefied undrained strength that the factor of safety, if there's no strength loss, the factor of safety is greater than 1, because you would use the peak undrained strength. But for 20% strength loss, the factor of safety ends up, for this particular example, being very close to 1. But if there's 60% strength loss, the factor of safety is significantly less than 1. And so there's a high risk of instability if the strength loss is triggered. Now, if you go for a slightly less steep slope, now, of course, the static shear stress becomes smaller. And so now The 20% strength loss has a factor of safety with the liquefied undrained strength greater than 1, so it's stable. And the one with 60% strength loss still has a factor of safety less than 1, but it's only slightly less than 1. So it's still unstable, so there is still some risk, but the risk is lower than the one that had a much lower factor of safety. And then, of course, if you make the slope even flatter, or you were to construct a buttress at the toe of the slope so that the shear stresses are reduced even further. So if you can reduce the shear stresses further, now even the material that has 60% strength loss potential, the factor of safety is greater than 1, and all of the scenarios become stable, and so there's very little risk involved. Now, if we now bring into the element of how brittle the material is, and brittleness is, you can have two materials that have the same strength loss index. Here I'm illustrating a 60% potential strength loss, but one where the strength loss occurs quite rapidly. This is the one in red. So you would regard this as being brittle, where the strength loss occurs at very small strains. But the other one shown in green is where the strength loss occurs more slowly and over a larger strain range. And so this would be considered more ductile. So they both have the same amount of strength loss index, or Bishop's brittleness index. So they both show a strength loss index of 60%, but clearly the material that is more ductile would be less of a risk than the material that's more brittle. And generally, low plastic materials tend to be more brittle, and high plastic materials tend to be more ductile. Now, if we introduce bonding or cementation, what tends to happen is light bonding can increase the peak strength. So here, if you look at the stress path, the stress path can actually exceed the critical state friction angle due to the bonding. And then once the bonding is broken, it then becomes extremely brittle and shows a higher strength loss index. So although they both have similar liquefied undrained strengths, the lightly bonded material is actually more brittle and shows a higher strength loss potential than the other material. And so you can often have no signs of distress prior to collapse because the material is lightly bonded, so it's not deforming very much. The strains are very small, but then once the bonding is exceeded in certain areas, then it can very quickly fail and rapidly develop into a failure mechanism with almost no signs of prior distress. Now, if you look at using limit equilibrium analysis, one of the problems if you use limit equilibrium analysis using the peak undrained strength, then often the results can be quite misleading if the material has the potential for strength loss. Because limit equilibrium analysis assumes a rigid, perfectly plastic material. So it assumes basically a single value of strength independent of straining. So if you have a sort of a traditional material that in undrained loading shows no strength at all, so it rises up to its peak strength, then limit equilibrium can provide a reliable estimate of the factor of safety. But if you have a material that is potentially strain softening with a significant strength loss, as I illustrate with the green example here, then you may have some elements of the soil that are before peak, but other elements that already have exceeded their yield and have already dropped down to their liquefied undrained strength. So the average factor of safety may be misleading in terms that some areas are already overstressed and have already passed their peak strength. So limit equilibrium using peak undrained strength ratio when you have a material that is susceptible to significant strength loss can be misleading and should be used with caution. So what's the risk of instability? And here, when you're dealing with large structures, you then have to evaluate the consequence if instability occurs. And so nowadays, for many tailings dam, you perform a breach analysis where you assume that if failure were to occur, you evaluate what the consequences are, both in terms of economic, environmental, and loss of life. And if the consequences are high, for example, significant loss of life, then you assume that strength loss can be triggered at some time in the life of the structure. It's impossible to design against all possible triggers with any level of confidence. So if the consequences are high, the only thing you can do with confidence is to assume that a strength loss will be triggered at some time in the future and design accordingly. If the consequences are low, in other words, no loss of life, little economic damage, etc., then it is possible that you could consider a detailed analysis to evaluate the risk of instability and whether or not it could be triggered. We don't have time to discuss that in detail, but the message here is that if the consequences are high, you must assume that strength loss will be triggered at some time in the life of the structure. So I've covered a lot of ground there. So to summarize, flow liquefaction is a significant hazard, especially for tailings dams. I've outlined a sort of a framework and methods that have been developed, and Bean and Jeffrey's book is devoted to going over a sort of a framework and methodology in great detail, and I recommend you read it. And so what we know is that loose, saturated, or near saturated low plastic soils at relatively low effective confining pressure in relatively steep slopes are the most prone to instability from flow liquefaction. And that in situ tests like the CPT with pore pressure or the seismic CPT tend to be the preferred in situ test to evaluate this behavior in combination with selective sampling and appropriate lab testing. And that you should assume strength loss if the consequences of instability are high. I know I covered quite a lot of ground there, but it will be recorded, and so you do have the opportunity to go back and sort of relook at some of the slides and study them in a little bit more detail. So I do apologize for some people if we did move rather quickly, but hopefully with the recording, you'll have time to look at it a little bit at your own speed. And also I've left my email address here, and so if you do need to contact me with any questions, do feel free to contact me. And thank you for your time and attention.